Bada boom boom, static shock. Okay, so let's talk about some circuits here and what we can kind of do with them. Let's just start off by drawing ourselves a simple circuit with a battery and a resistor. So here's my long edge of the battery, and I'm going to go around with a wire. Here's a poorly drawn resistor, and here's my short edge. Okay, remember the long edge of the battery is positive, the short edge is negative. Let's just say this sucker is like a 9 volt battery. Like I said, down here, this is our resistor. It has some resistance R, okay? Now, when we talk about a circuit, we need to think about how this current is flowing around it. The current is, coming out of this battery. It's coming out of this potential source, and it's flowing around the circuit. But which way is it flowing? Is it flowing clockwise or counterclockwise in this example? Well, for this, we can think back to what we did last unit, and we can think about how positive charges are our test charges. When we go back in history and think about this, we really didn't know anything about positive and negative charges. We didn't know about protons and electrons. Like, that wasn't a thing at this point in time, the 1700s, when electricity like this in circuits was being discovered. And we can actually blame one of America's founding fathers, Ben Franklin, for messing this up. What Ben Franklin proclaimed was that we have some positive and negative charges, which is awesome, and that the positive charges are the ones that are racing around this circuit here in a current I. But if the positive charges are moving around, that means we're moving protons, which, if you have the ability to move protons around, you have a bit of an issue with the nucleus of the atom. So while Ben Franklin was wrong here in saying that the positive charges were being moved around, quite frankly, it didn't really matter what he picked, because mathematically we could just kind of like multiply by -1 and just flip them. And potato, it doesn't really matter. We call this, though, the traditional current, because this is traditionally what physicists have thought of as going on and how our mathematics will work itself out. Okay, it's the conventions that we have picked. If you wanted to, and very few people do this, you could think about the current as the electrons flowing, okay? We will not be using this. This is commonly referred to as the electron current, and it is opposite of the traditional current. We're not going to use that one, okay? We're going to stick with the traditional current because that's just the way we've done things forever, and quite frankly, it doesn't matter, okay? So don't go nuts about that, okay? In this case, though, the direction the current is traveling is the positive direction of that current, and that is the traditional current there. Now, if we think about this, on our battery here, our positive side, our high potential, is at 9 volts, and our low side is at 0 volts. Well, that means as this current is going around, as these charges are going around, they need to go from a high potential to a low potential. And how can they do that? How can they get some amount of work to be done on them, or to be done? Well, the way we do this is using Ohm's law. And this is one of the most important things that we'll be using throughout this unit. And what we'll actually do is we'll actually just take this current and go around the loop, okay? And basically, every time we hit a component of a circuit, such as the resistor right here, there is a voltage drop across it. Remember, that voltage drop is the potential. So whenever we go across a resistor, we have a voltage drop equaling to the current across it multiplied by the resistance of that resistor. This is Ohm's law, V equals IR. And in this case, because we only have one resistor here, we can just say, hey, the voltage here is 9 volts. Let's give the current a value. Let's say the current is 3 amps. So we could say the current here is 3 amps. Now, because we only have one unknown in this equation, we could solve for R. We could say 9 volts equals 3 amps times some resistance R. And when we divide 9 volts divided by 3, we'd find that R would equal 3 ohms. So this is Ohm's law here. It's a pretty straightforward law. If we look at it, it is very nice and straightforward. One nice feature about it is that V equals IR is linear. So what we see here is that if we have a voltage on the y-axis, this is like y equals, and now we can put in our values here. If this is our current, so actually the way we're going to write this is like x times m, then if this is some straight line, the slope of this is actually the resistance, which is a pretty cool thing. Now, if we have a nice linear function like this that obeys Ohm's law, we call those resistors, or whatever it could be, some substance, we call them ohmic in nature. Okay? Now, things don't have to be ohmic. Things could actually go like this. They could actually whoosh, go something like that. And if we look at this, if we look at the tangent lines here, we see that the slope is changing throughout this. And what this means is this is a non-ohmic device. You may be thinking like, well, what kind of weird thing would do that? Light bulbs do that. Incandescent light bulbs do that. And the reason being is that whenever those incandescent light bulbs, those old school ones with the filaments on the inside, when they get very, very hot, the resistance changes within them. They actually get more resistance. It kind of changes the circuit property a little bit, as we'll see later, and it makes them non-ohmic in nature. So if you see something that's non-ohmic, it's going to have to obey kind of a curved graph on this for a VI graph. A ohmic will still be a nice linear straight line, which is a great thing for us, okay? But this is Ohm's law. And like I said, the way we get it is we're just thinking about dropping these potentials across this circuit. If you want to get technical, and we'll do this later on, we can actually think about we're making the Kirchhoff loop and going around and getting this same equation, okay? And this would be like the easiest Kirchhoff loop you can. We'll talk about Kirchhoff's loop later. Super fun thing. But this is just how we talk about basic circuits. Remember, we are thinking that the positive charges are moving as a traditional current direction. And with Ohm's law, V equals IR, we can solve for missing components of the circuit by looking at voltage drops across a resistor. So with that, we'll be taking a look at some more detailed circuits later on. What happens if we have more than one resistor, together, or like in different branches? What happens to something crazy in our circuit? We'll be taking a look at all of that as we continue on in this. But until next time, adios, and take it easy.